This is the Module 4 video introducing the Diels Alder cycloaddition. This is a historically important reaction which is still widely used today for synthesizing cyclohexenes. In this course, the Diels Alder cycloaddition will be a topic in which we will integrate the concepts of molecular orbital energies with specific thermodynamic and kinetic data. And then in Module 4b, we will explore the stereochemical aspects of the Diels Alder cycloaddition. In a prototypical Diels Alder cycloaddition, 1,3-butadiene reacts with maleic anhydride or other alkenes, generally with electron-withdrawing substituents. Most Diels Alder cycloadditions proceed through a mechanism that is a single step. As I scroll down the screen to the molecular orbital diagram, for 1,3-dienes, in which the two alkenes are conjugated, the molecular orbitals are often referred to by the Greek letter psi. And so instead of two separate pi bonds, these act as a unit, as a psi-diene. For 1,3-butadiene, we will account for the two electron alkenes. So two electrons fill the lower energy orbital psi-1, and two more electrons for psi-2. The orbital at minus 6.1 electron volts is the highest occupied molecular orbital. Then psi-3 is the lowest unoccupied molecular orbital. For maleic anhydride, there are two electrons in the single alkene, and so I add them in this position. For maleic anhydride, the electron-withdrawing carbonyl groups lower the energy levels of the HOMO and the LUMO. Compare these energy levels for maleic anhydride with the parent alkene ethylene, in which the HOMO is now at a higher energy of minus 7.1 electron volts. For Part B, we will discuss in class which orbitals react in the Diels Alder cycloaddition. On the next page of the worksheet, here is a second example of the Diels Alder cycloaddition. This transformation was discovered about 50 years after the first Diels Alder cycloaddition because it requires forcing conditions. 450 Kelvin is 177 degrees Celsius, and this also requires high pressure. This is a Diels Alder cycloaddition with a much higher kinetic energy barrier. And later I will present some specific information on that in Part 3 of this worksheet. For now, based on the molecular orbital energies, we'll discuss how we can explain this higher kinetic barrier. In Part D, I present some kinetic and thermodynamic data for a conformational interconversion. You studied conformations in Chem 202Z. For 1,3-dienes, the more stable conformer has a sigma bond with the alkenes trans to each other, whereas the reactive conformer for the Diels Alder cycloaddition has a sigma bond with the alkenes cis to each other. There is an energy barrier, delta G double dagger, which is the energy of the transition state for the sigma bond rotation, which is approximately 30 kilojoules per mole. The thermodynamic information is that delta G is positive 15 kilojoules per mole. This is an endergonic transformation. The Gibbs free energy equation links temperature and the equilibrium constant. Delta G was actually calculated by measuring the equilibrium constant, but we can turn this equation around to solve for the equilibrium constant if we are given the free energy of the reaction at a specific temperature. At approximately room temperature, or 300 Kelvin, the equilibrium constant is very, very low. This number means that only 0.2% of a sample of butadiene is in a conformation that can undergo Diels Alder cycloaddition. Scrolling down the page to part E, I will briefly mention orbital symmetry. So notice how the termini of the reactive orbitals have the same symmetry, so that symmetry matches at the positions where carbon-carbon bonds form. Specifically, the polarity of this p orbital component is in symmetry with a p orbital component of the pi star orbital, and likewise there is symmetry between the other p orbital of pi star with the terminal p orbital of psi 2. This explains why four-membered rings do not form in the Diels Alder cycloaddition. For four-membered rings to form, this would require orbital overlap between these two p-oriented orbitals, and notice that they do not have the same symmetry. There are actually two reactive orientations, so that the collision can occur with exo orientation or with the diene flipped over relative to the single alkene, which we call an endo orientation. The significance of exo and endo will become apparent when we get to Module 4b. This concludes the introductory video on the Diels Alder cycloaddition.